show up to class with Jeff on my t-shirt.
Oh, that is a t-shirt?
Like Jeff on the front.
And it should be something ironic, like always on time. Right? No. I don't know who we're talking about. Who could it be? I don't know. Anyway, I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for these students and this class, and that we can talk about manifolds for a few hours a week, Lord. You know, I pray, Lord Jesus. Amen. This is the verse which was suggested to me today. I will allow it. As each one has received a special gift, employ it in serving one another as good stewards of the manifold grace of God. Yes, it's good. I should actually start featuring all of the verses in the KJV which use the word manifold. Is this KJV? NSB. Oh, it survived the 95. It survived the. It's funny, like, it's so obvious that the KJV has had vast influence on all the English translations, because despite the fact that there's more natural language for many verses, they have kept the KJV phrasing, just because to do otherwise would be to outrage people's favorite verses, you know, like various things. No, it's melting. All right. All right, so let's see here. I wanted to do a few different things today. All right, so let me get started. I wanted to start actually with, this is the danger part because I haven't even written anything out, so we'll see how this goes. But I wanted to actually calculate the Lie algebra for a particular Lie group. And this example's in the book, but I'm not looking at the book because I'm trying to do it of my own way. So let's calculate the tangent space at the identity to the orthogonal group. So the orthogonal group is A in Rn by n such that A transpose A is equal to the identity, right? So this is, of course, a subgroup of the general linear group, right? And I think we even calculated its dimension the other day. Whatever. Okay, so here's the thing. If you want to understand the tangent space to the identity of a Lie group, all you got to do is think about a kind of sketchy picture with eins element, which here is the identity, right? And then really we're just interested in, like, what is the condition that we are forced to deal with on the identity for a vector at the identity, right? So if this is a curve that goes through the identity, I can take a typical curve through the identity and I can write it like this. Gamma of t is equal to the identity plus t times b, right? And if I do that, where I'm making the standard identification of like the standard matrix units with the standard derivations with respect to the usual coordinate map, with that identification being understood, we see that gamma prime of 0 is b. All right, so b would in fact be an element of the tangent space at the identity to the orthogonal group. All right.
Gamma prime of I or 0?
Gamma prime of 0. So gamma is a mapping from the reals into, ON over here. Okay, so here's the deal. What we have, well, first of all, this is gamma of t is where? Gamma of t is an element of ON. All right? Now, I don't think this is actually entirely true. Maybe he has more fine print. I thought this was too easy. What I usually see done, instead of this, is I see this. e to the tb. Let's do that. Because I've talked to you guys about the matrix exponential before. Have I talked to you?
I was gone one class period.
But you're gone one class period. Yeah, it never happened this semester, though. There is a thing called the matrix exponential, which you would have talked about in my linear algebra, but you did not have my linear algebra. All right, fine, crash course. E to the m is equal to the identity plus m plus 1/2 m squared plus da da da. So in short, it's the sum n equals 0 to infinity of m to the n over n factorial. This is the matrix exponential. You can prove that this thing converges. That's the kind of thing I would do in advanced calculus, which is, as I was saying, partly an analysis class. And unintended plug, but there it is. So anyway, long story short, the matrix exponential has beautiful, interesting properties. Here are some of them. E to the 0 is equal to the identity matrix. And another really cool property of the matrix exponential, and this one is by no means trivial. This one actually is kind of hard to prove. This is probably in your homework, because if I saw a homework problem somewhere with it, I'll make you prove it. But the determinant of the exponential of a matrix is actually equal to the ordinary exponential of the trace of the matrix. That's pretty simple to prove for like a diagonalizable matrix, but it is in fact generally true. It's easy enough to verify for the Jordan form of the matrix, and since any matrix is similar to a Jordan form, proved. But so that's an identity, which is true. More to the point, e to the m times e to the minus m is equal to the identity. So like the determinant, any matrix, the exponential is invertible. The matrix exponential of any matrix is an invertible matrix. All right, more to the point here, finishing my 2-minute crash course on the matrix exponential. The derivative with respect to time of the matrix exponential of e to the ta, where a is a constant matrix, all right, is just the following. And you can actually derive this, and I do derive this like, typically in like a differential equations course when I teach it. You just put ta up in here, and you just differentiate term by term. Okay, this can be proved that that's how the differentiation goes. But anyway, it just is this, a e to the ta. That's how it works out. Okay, so that's the matrix exponential. And the so the matrix exponential is a nice candidate for, so that this might be legitimate. I don't know. I'm not convinced that gamma of t is actually, so this is like the thing. I wrote this over here. Gamma of t is an element of on for gamma of t equals to I plus tb, and I just don't believe it. I just don't believe it. But I do believe that it's possible for, if we let gamma of t equals to, I mean, maybe it's true. I don't know. I'm not sure. I have a bad feeling about it. E to the tb, we could make that an element of on. See, the thing is, e to the tb, it's got so much more in it than just I plus tb. It's I plus tb plus 1/2 t squared b squared plus dot 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 dot. All right. Anyway, actually, more to the point, and this is looking into the future, like near the very end of the course. Chapter 20 in the book, it circles back to Lie groups and Lie algebras, and it uses all the materials on flows and things that we're about to half cover today. And it uses those to define the exponential on a Lie group. It's like the exponential on a Lie group you end up defining as, in terms of the flow of a particular, along a particular, you look at one parameter groups through the identity, and you can use those to like define the exponent. There's a way of defining the exponential for an abstract Lie group. And when you do that, it turns out, lo and behold, it is the matrix exponential. All right, so the theory for this is really in chapter 20. So I'm putting the cart before the horse, but I think at least it's true. So anyway, so if that's the case, what does this mean? This means that e to the tb times e to the tb transpose should be equal to the identity. All right? Also notice that like gamma prime of 0 is what? B e to the 0 times b, right? Which is just b. So b is a typical vector in the Lie algebra, which we identify as the tangent space to the identity of the Lie group. All right, great. Now, yet another thing about the matrix exponential. It is an identity which you can identify, you can prove. But here it is, e to the tb times e to the tb transpose is equal to the identity. So like e to the m transpose is equal to e to the m transpose. That follows from like taking the transpose of this series, which you can do term by term, because you can do it for a partial sum of the series and then take the limit as the limit of the sequence of partial sums goes to infinity, and you maintain that identity. But anyway, now we have this. Differentiate. What do you get? So differentiate this with respect to time. What do you get? You get b e to the tb times e to the tb transpose plus e to the tb times b transpose e to the tb transpose equals to d dt of the identity matrix, also known as 0. All right. So, and we really want to plug in time equals to 0 into our derivative because that's what we're interested in, right? So take all this, evaluate it t equals to 0. What do we get? We get that b times I plus b transpose is equal to 0. All right, so all of this together being said, this shows us that little on is equal to b in Rn by n such that b transpose is equal to minus b. So this is the Lie algebra of the orthogonal group. You can also, of course, talk about like the special orthogonal groups. I think in your homework, I think one of the homework problems I assigned you guys was to calculate the Lie algebra for different Lie groups. I believe. I think I assigned that problem.
Which one?
I don't remember which one, but probably 5. Yeah. So like this, you can if you find this helpful, if you find it helpful, feel free to take this approach. Assume that we can write a curve through the identity as the exponential of something in the Lie algebra, and you can use that to derive that problem. That's fine by me. Okay. Although I think technically we're using chapter 20 stuff. Now, so like so generically speaking, this is what happens, guys. You've got a Lie algebra frac g, and you run it through the exponential, and you get out, you get out g, I guess we could say g prime, which is like a subgroup of, I'm not even sure it gives you that, a subset at least, a subset of g. So the exponential doesn't have to like be onto the Lie group, but it will at least map to the identity and to stuff close to the identity. And the image of the exponential at least can be used to generate the connected component of the identity that we talked about before. But it won't generate, of course, like the other part. So ON, remember, we talked about this before a little bit. It's the union of what? There's like SON, right? Union with, we could call it minus SON perhaps. So these guys, determinant of A equals to 1. These ones, determinant of A equals to minus 1. Remember that the condition A transpose A equals to the identity forces the determinant to be plus or minus 1. Did I say that in here? I'm not sure. I'm teaching linear algebra right now, and this is an example I did in there. So if I've only done it in there, my apologies to you guys. I remember taking 2 courses from my advisor, Dr. Fulp, once upon a time, and he would start using stuff in one class and the other. And I was in both classes, so I knew what was happening, but I was like, so I'm sympathetic. Anyway, so if you think about this, would SON have a different Lie algebra than ON? Like, essentially, SON, right? It is one of the connected components of ON. All right? So it's the same dimension. Oh, by the way, this is a nice way to calculate the dimension of the Lie group, because the dimension of the Lie group is the dimension of the Lie algebra as a real vector space. So you can find a basis for the antisymmetric matrices to calculate the dimension of ON here. Okay. But notice this identity over here. The determinant of the exponential, see that? What's the trace of B here? No idea. So what is the trace, though? Do you know what the trace is? Sum of the diagonals, right? So what's this condition right here tell you? It tells you that B ij is equal to minus bji, right? For all components. So what happens when you got ii? So an antisymmetric matrix automatically has zeros down the diagonal. So it's automatically traceless. See, the trace is 0. So what does that tell us? That tells us that if we have, if you have a B in the Lie algebra little on, then it's also in the Lie algebra for little son. So like what I'm saying is that this is actually equal to little son. So this is the, you notice there's a capitalization. You guys got to see what's going on here. So we're using lowercase letters for the Lie algebra. We use uppercase letters for the Lie group. Okay. The same thing goes with this, like the Lie algebra, the general linear group, GLNR, versus GLNR. Lowercase for the Lie algebra, uppercase for the Lie group. And to get from here to here, exponential. The matrix X. Now it doesn't go on, it's not on 2 again, but it will at least give you an image which is in the connected component of the identity. And essentially the proof that the exponential of a matrix is in here is, well, there's various ways to look at it. This identity shows you, right? The exponential of any matrix is invertible, right? So essentially there's, if you have a curve in GLN, e to the TA, right? Like t maps to e to the TA in big GLN. It doesn't really put any kind of restriction on A whatsoever. A could be anything. So that's why the Lie algebra of the general linear group is just n by n matrices with no restrictions. But when you look at a subgroup of GLN, like the orthogonal group or the special orthogonal group or the other ones in your homework, then, anyway, I'll shut up. Otherwise, I'm just going to do that homework problem, which is not interesting. I should leave that for you guys. So I was hoping Jeff would get here and then I would start new material, but so if I teach Jeff a class another semester, what I'm going to do is I'm going to create a fake starting time and tell it to him. And then I'll plan to start the class 30 minutes after that time. It'll do it. It'll work. Okay, so here we go. Chapter 9 then. So this is on integral curves and flows. So I'll just give you, the quick version of this chapter here today. If I can find I did write notes. Tell me I didn't bring my notes. Haha! I have them. So in short, what is done in this chapter is it is shown that every smooth vector field on a manifold determines a unique maximal integral curve that starts at each point in the manifold, and the collection of all such curves, such integral curves, determines what's called a maximal flow. So, you have physics? 232? That's right, we took it out of the curriculum because we're dummies. But in physics 232, you learn about field lines to electric fields, and these field lines would be what we would think of as integral curves. So like a field line to a vector field, they're a set of curves which line up with the direction of the vector field. All right, that's called an integral curve. And, well, let's just get into it. So, definition. If V is a smooth vector field on M, then integral curve, I guess I'm missing a word, then an integral curve of V is a differentiable curve gamma from J, which is an interval, all right, to M, such that gamma prime of T is equal to V at the point gamma of T for all T in J, which again is a subset of the reals. It's an interval. Moreover, if 0 is an element of J, then gamma of 0 is equal to the starting point. Starting point of gamma. All right. So let me just do some examples, because I've given you guys some homework, so it would probably be nice if I did some problems in class, which are like your homework. I know it's a weird idea, but I'll do it. So if we look at the vector field partial x on R2, then we can ask, what are the integral curves of this vector field? All right? We're going to derive that they're horizontal lines. All right, which you can kind of anticipate, because you know what if you visualize this as I hat vector field, if you like, it just points to the right, right? So the curves which line up with it should be horizontal lines. Let's work it out though. So here's what we're going to do. We're going to say that gamma prime of T is equal to dx dt partial x plus dy dt partial y, and that is going to be equal to partial x. Now this is all at gamma of t, which is equal to x of t, y of t, all right? But I'm not going to write all that out on all of those because it would be annoying. All right, and I'm also using x and y in like at least 2, possibly 3 different ways in this calculation. I hope that's okay. All right, so what does this mean then? We're actually needing to solve. So we're up against dx dt is equal to 1, and dy dt is equal to 0. These we can solve by integration, right? So this tells me that x is equal to t plus a, and this tells me that y is equal to b, where a and b are a constant. Put those two things together, we've got gamma of t is equal to a plus t, comma b. that is the integral curve. What's its starting point? AB. So, and this is actually what we will learn. This is a complete vector field. A complete vector field is one for which the integral curves have a domain which is the whole reals. I'll show you an example in a minute or two where, although it doesn't, there's no reason to see it from the vector field itself, but because of the quirks of the structure, the calculus, we can't take the domain of the vector field to be the whole real line. And when you're forced to make the domain of the integral curve not be the whole reals, it means it can only be like maximally extended to a certain amount. And there's about a good 3 or 4 pages in chapter 9 which deal with an apparatus to make that formal and careful, which I'm not going to go over in class. Something called a flow domain. He's got this script D thing he starts talking about, but we won't get into that, I don't think. Now, example 2 will require a little bit more trickery. So example 2, one of my favorite vector fields, W. And we're going to do minus y, partial x, plus x, partial y. And we're going to look for W of gamma of t equals to, gamma prime of t, right? Again. So this time, we've got our gamma prime, I'll just write it out again. So by the chain rule, that's dx dt partial x, right? Plus dy dt. I'm not sure it's the chain rule. It's just how the derivative of a curve interacts with the chart domain, as we've worked this out before, back in like chapter 3, 4, maybe. So that is going to be equal to minus y partial x plus x partial y. All right, so the deal is, to find the integral curve, you just have to solve. See, every integral curve relation suggests a particular system of differential equations, what's called an autonomous differential equation. The reason it's autonomous is because the derivatives just depend on the coordinates and not time. So we got like dx dt is equal to minus y. And we also have dy dt equals to x. Have either one of you taken differential equations? Okay, good. So I've got nothing to unlearn. If you have nothing to unlearn, you can only learn. It's good. So to solve this, what I would do is I would plug one of these into the other. Probably I'll put this one over here and see if I take this and I plug it in there, that gives me dy prime prime. I'm an idiot. D squared y dt squared. Oh, come on. D squared y dt squared. Let's go. Minus y equals minus y.
In the integral here, are you saying that the integral is equal to a plus t comma b, or gamma is equal to that?
Gamma.
Curve.
Oh, that's not meant to be an integral. That was actually, it does look like an integral though, but what I was aiming for there, believe it or not, was one of these guys.
Okay.
But it did very much look like an integral, and I was talking about integral curves, which is probably why I wrote it. Fair enough. So, all right, you guys, we don't need anything sophisticated here. We need guessing. The fundamental method for solving integrals is guessing. What function, when differentiated twice, gives you back minus the function again?
Sine, cosine.
Sine and cosine. Fun fact, the theory of differential equations says that the arbitrary solution to the general linear equation of order 2 is a linear combination of the fundamental solution set. If you have two linearly independent solutions, then the general solution has the form of a linear combination of said solutions. Since sine and cosine are linearly independent, and since they're never both 0 at the same time, the general solution looks like this. Y is equal to, we'll say a sine t plus b cos t maybe. Right? And then once you say that, a and b are constants. You can try it. Differentiate this twice. You get back where you started. It works. And once you write that down, x is easy to find because x is the derivative of y. So x apparently is a cos t minus b sine t. There you go. Your integral curve to this here vector field is a cos t minus b sine t, a sine t plus b cos t, with starting point gamma of 0 equals to a comma b. So again, this is a complete vector field because the integral curve has a natural domain of the whole real line. And a and b, both of these examples, a, b is arbitrary, right? You can find an integral curve which goes through any point. Agreed? Now, what are these? Like the other way you could have solved this would have been okay, so admittedly, I was happy you guys didn't know differential equations, because if you did, you might not solve it this way. If you knew a lot of differential equations, you might say, oh, y is equal to like r, I don't know, r sine of t plus phase angle phi. And then x would be like r cosine of t plus phase angle phi, right? And then you could easily see that x squared plus y squared is equal to r squared, and you're doing nothing but parametrizing a circle of radius r centered at the origin. Indeed, that is the case. The integral lines of this are exactly concentric circles of the origin. These are your integral curves, because what w really is, in the language of my Calc 3, is, I think it's just theta hat. It's the gradient of the angle function, if you like. I could be wrong about that. I might be wrong about that. That seems wrong. It's something like that, though. It's definitely pointing in that direction. So let me put some quotes on this, because I'm not sure it's true. Probably should make them approximate quotes. Whatever. Yeah, okay. Doing some sort of like ancient language or something. Proposition 9.2 tells you that if you have a vector field and you got a point on the manifold, then there exists an epsilon in a smooth curve defined from minus epsilon to m such that it is the integral curve of v. All right, so like if you've got a vector field, you can find integral curves. And that's proposition 9.2. It's an existence theorem. Then proposition 9.3 says that you can rescale the vector field if you want. And then there's a natural connection between the rescaled vector field and basically you can take if you multiply a vector field by a number, then you can take the integral curve that you already had and modify it a little bit, and it'll be integral curve for the rescaled vector field. And you can also translate the integral curve, and it'll still be an integral curve for the same vector field, but the domain's a little bit wonky. Finally, if you have a diffeomorphic, if you have a smooth map between manifolds, and you have vector field x and vector field y on m and n respectively, then x and y are f related if and only if the f composed with gamma is integral to y whenever gamma is integral to x. So there is a way of characterizing the f relatedness of vector fields by basically saying that they map integral curves to integral curves of the vector fields. All right, so in some sense what that's saying is that integral curves to vector fields it's almost another way of describing the vector field, really. You might even say that. It's certainly true in a physics book. Like if I give you a picture of the field lines of the vector field, I'm pretty much defining the vector field. That's true in Calc 3 too, I guess. You know, if you have pictures of the field lines of the vector field, that pretty much defines the vector field, doesn't it? The magnitude's a little sketchy though. So let me just talk about the proof to 9.6 a little bit. There's a calculation here I wanted to do for you guys. Proposition 9.6 proof. Calculation. So here's the setup. We have f, a smooth map from M to N. And we have x, a smooth vector field on M. And y, a smooth vector field on N. And then the claim is that x and y are f related if and only if f composed with gamma integral to y whenever x integral to, gamma integral to x. So I will just look at the forward direction of the proof, but I think the calculation is worth our time. It'll take us about 2 minutes and well worth it. Gives you guys another chance to see the F-related definition in action. So let's do it. So we're assuming x and y are smooth vector fields, F is a smooth map, and we're also going to let gamma from J to M be integral curve of x. And we'll define sigma equals to the composite of f with gamma. Now we will calculate the derivative of sigma prime of t. All right, so sigma prime of t is f composed with gamma prime of t, right? But we know how that goes. Chain rule. So this is df, right? df at the point gamma of t of what? Of gamma prime of t. All right, but what's that? We got ourselves df of gamma of t, and let's see, your gamma prime of t, remember, is the integral, it's an integral curve of x, right? So by definition of integral curve, we can trade gamma prime of t for simply x at the point gamma of t. You guys got that? Does this make sense? So integral curve means that the vector field is equal to the velocity vector of the integral curve. This is the velocity vector, integral curve, the vector field at that point. That's just definition of integral curve. But you guys remember last time we talked about f related. So that if x and y are f related, this is what? That's exactly, where was I? Y of f of gamma of t, by the definition of f related that we looked at last week. And then, since y, but that's what? Remember, sigma is f composed with gamma? So this is exactly y of sigma of t. So that proves that the derivative of sigma, the velocity field to sigma, matches y at sigma of t. So what this is saying, like pictorially, if this is m and this is n, right? Then you've got, this is your gamma and this is your sigma, right? And x would look something like this if I was to plot it. And y would look something like this if I was to plot it. And of course, F goes from here to here. That brings us to talking about flows. What is a flow? So as is usually the case in math, like you start with one concept and you build another, right? And then what do? You say, well, what if we just had the other as the starting point? So that's what's about to happen, is like we're essentially erasing the vector field and saying, what if you just had the flow? Well, I guess we're not quite there yet. First, we'll build the flow from the vector field, and then we'll do the erasure I was just talking about. All right, so come on. Uh-oh. Well, it's okay. So what I was saying, Jeff, is that the x matrix exponential here is actually, that's like chapter 20 technology. But I'm letting you guys use chapter 20 technology for like the chapter, I don't remember, earlier chapter homework. It's just convenient to write curves through the identity of a Lie group, a matrix Lie group actually, in terms of the exponential of some matrix. It turns out that the matrix being exponentiated is one and the same as the Lie algebra of that particular matrix Lie group. Exponentiation is essentially the bridge between Lie algebras and Lie groups. And actually, if you know the Lie algebra, if you can define the Lie algebra, if you have all of its so-called structure constants, basically, that's a roadmap for how to commute matrices or not, then from that you can build the group multiplication, at least in the connected component of the identity of the Lie group.
Basically here we have curves whose slope equals at every point the vector.
Oh, right, yeah. Right, so like here, those are the integral curves. And so, the vector field I could visualize like this, right? I mean, it's very silly, but yeah. And this one, I didn't attempt to draw the vector field, but if you look, for example, at like 0, 1, we'd have, let's see, 0, 0, 1 would be here, and it would be something like this, right? And then if you go to 1, minus 1, 0, you've got something like that. If you go to 0, minus 1, you've got something like this, right? If you go to 1, 0, you got something like this, and so forth, right? And I can make those pictures as busy as you want, by adding more and more and more vectors in the vector field. Of course, here I am also using the identification of the geometric vector corresponding to the derivation, right? We do sometimes prefer to look at vectors as derivations on smooth functions as our primary viewpoint. Okay, but anyway, flows. Let's talk about flows. Flows. Come on. So here's the definition for V, a smooth vector field on M, and P, a point in the manifold, such that the unique maximal integral curve starting at P is denoted theta parentheses upper P. That's a mapping from R to M. Now here, okay, so I'm assuming that this is complete vector field, okay? again, to be fair to John Lee, he does have a more nuanced approach in the chapter. He motivates the concept with complete vector field, and then he admits that not every vector field is complete, and he builds this local flow domain contraption to take care of that. And at the end of it all, everything I'm defining for the complete vector field can also be defined for the more nuanced vector field, which has an annoying smaller domain. The integral curves have a smaller domain. All right. And furthermore, theta sub t, so don't worry, why have one notation when you can have three? Theta sub t of p is theta up parentheses upper p of t. All right, and if I can hazard a picture here, what's going on is something kind of sort of like this. So here's your manifold. Put a hole in it. There we go. That's how you know it's a real manifold. It's got a hole. So I never put holes in my manifolds in advanced calculus. That's one of the big differences between the courses. So this is the point P. Then over here, you might have theta t of p, and perhaps over here, if you might have theta sub s of p. And guess what? Over here, if you keep going, maybe I'd have theta s plus t of p. But the way this works is that theta sub s plus t of p, you could also get by theta, oh, let me not try to do that. No. So that's a picture. Stick to my notes. No. I'm about to do something really stupid. I wasn't trying. Stop. Stop. All right. So this is the flow. So this is like the integral curve, right? And if you go along the integral curve, you can kind of imagine just sliding along the manifold, starting with p. Basically, p is where t is equal to 0, and you can just kind of go along, right? You almost think of it like a coordinate line that's based on the vector field, right? Sort of like that. Okay, so this is something we can define for a given vector field, because for a given vector field, we just described how you find the integral curve by solving a system of differential equations, all right? And there's existence and uniqueness theorems that are shown to you in chapter 9, which prove that essentially there always exists a solution, all right? Great. So,
why is it unique and maximal system?
Oh, that's also in the theory. There does exist a unique maximal curve. So in the larger discussion of the not complete one, there's like a maximum. I think the largest domain you can have that includes 0 being the point, the starting point, and goes away from the point. Like you can't. There's a notion of maximality there that, again, I'm not going to get into. But in short, what I'm telling you, and I'm not very proud to say this, but read chapter 9. Yeah. Okay, so where was I? Oh, yes, definition. Global flow on M, all right, is a continuous left R action, as in left group action, theta, from R across M to M again, all right, such that for all S and T in the reals and P in M, we have theta of t, comma, theta of s comma p equals to theta of t plus s comma p, which is what I was about to write down there. All right. And also theta of 0, p is equal to p. So this right here, there's no vector field in sight. See that? No vector field here. It's just a continuous left R action on the manifold. So remember we talked about group action? So that's what I'm referring to here. Notice that this has the axiom. This basically is the composition axiom, right? So like you can act by S first and then by T. That's the same as adding S and T and acting. That's the composition axiom in our current notation. And this is the eins element of the group, acting as the identity map on the manifold. Those are the two things we need for a group action. Now, so once you have this, then we can do other things. So here's the thing, is given, this global flow as above, right? You can define theta sub t as a mapping from the manifold to the manifold by theta t of p equal to theta of t comma p. Okay, great. And if theta t, if it's a continuous action, that means theta t is a homeomorphism. If it's a smooth left R action, that would make this theta t actually a diffeomorphism. And we can also define theta upper p from the reals to m by theta upper p of t equal to theta tp. All right, so we can define these curves on the manifold using the flow. Right, fix a point, see where it goes. Basically, the curves that the flow are defining are just the orbits of points under the flow. All right, these are orbits. I mean, the image of this thing is orbit of P under group action. All right, great. Then proposition. Oh, I guess I need another definition before I tell you a proposition. So let me put the definition in the middle of the board if you guys don't mind. Definition. Thank you. Girls, I tell you. Where was? Let's go indeed. Oh, come on, where'd you go? Don't hide from me now. Oh.
We're in page 209.
I'm 212. So, wait a minute. Maybe I'm on 209. Well, that's depressing. But what I was looking for here was actually 210. Definition VP equals theta upper P prime of 0. So this is the infinitesimal generator of the flow theta at P, let's say. All right. And then and then of course you can define a vector field in this way, right? P maps to VP. that defines a vector field, right? That defines a vector field on the manifold. And so proposition 9.7, what it says is simply that, VP equal to theta P prime of 0, it basically defines a smooth vector field P maps to VP. Let's call that vector field V. So that is, V is a smooth vector field on M, whose integral curves are what? Precisely the orbits of the flow. Now, I am assuming here that to get a smooth vector field, we do need a smooth flow. But if that's smooth, then that begets the smoothness that you want for the vector field generated. All right, so if we go back over here to example 1 and example 2, we can see example 1 and example 2 in a different light. All right? Like, we can go back to example 1 and example 2 and give a flow on R2. We can define a global flow on R2 for which V and W are respectively, good grief, the infinitesimal generating vector fields. All right, so like example 1, what's the flow? What would you do? What would you say here? The flow would be what? Theta of, let's see here, T comma P equal to, let me not write something stupid. Oh, my bad. It's more fun. It's better to write it in the other notation. Like this kind of is like the better notation to use. So like let's do it that way. So theta sub T on the point AB equals to what? Mm-hmm.
Is it x minus t and y?
Well, we want the integral curves of, well, let me just do it. So it's a plus t, or if you like t plus a comma b. See, then theta at the point a comma b prime of 0 is exactly, partial x, because it's just 1, 0. So in fact, this is the infinitesimal generator of this global flow on R2. Similarly, we can, let's say, eta sub t of, AB, we can let be
Negative b a.
negative b, no, not that. No, just these up here are the, you're looking for. So you do, let me just make it a little bit more transparent what I'm doing. Cosine t minus sine t, cos t, 2 by 2 matrix times AB.